their intelligence is wanting. Why else do people get into accidents?
Alertness, probably a lot.
Huh?
Alertness, like distractions.
Right, they might be texting.
Right.
Or talking on their cell phone. What else? Huh? Netflix? They're watching Netflix. Do you seriously watch Netflix while you drive?
Oh my God.
No.
It's not acceptable. Okay, I'm now so incredibly terrified. I'm going to bring in the videos about like even how bad it is just to send a text like OMW. And the
I know, I saw the videos already.
And yet you're watching Netflix.
It's the only time I have to myself.
I think watching Netflix might be better than texting.
Huh?
If we're comparing different bad things, I think texting might take more attention than watching Netflix.
What?
No.
You can
Yeah,
this is how I drive.
exactly.
Okay, no.
No. Don't drive now.
And then I just like,
What kind of car do you drive, and what do the lights on? Every time I see you, I need to go the other direction. Yeah. Okay, I'm now officially terrified. All right, so
Oh my God.
so we agree that things like intelligence, alertness, whether they're distracted, doing something else, maybe they're high, drunk, buzzed, right? Or you ever had issues with people who drive like crap because they don't know where they're going?
Yes.
What is it with people in Atlanta? They're like, I'm over here in this lane. The exit is over here. There are 3 lanes of traffic.
Yes.
And I'm like, what? Like, if you want to get off the exit, you need to be in the you do that too, don't you? Because you're freaking watching Netflix. You totally do that. All right, now every time you see someone do that, I want you to shake your fist and go, Netflix! Because now we know what makes people do that. It's Netflix. Eric. And then, let's just forget turn signals. Like that's like they don't even know what that stick on the side of the. Oh my gosh, whatever. Okay. So if you don't know where they're going, sometimes and around here you run into where the roads suck, right? And people are driving too fast for the road, and then it's like they just peeled the top of all the road, and it's all bumpy or whatever, or it's got a lot of gravel. They don't know what they're doing, or they don't take care of their cars, so their tires are all slick, and then it rains, and they slide all over the place because they don't have any tread left on their tire. Or oh my gosh, I'm dealing with this one. Driving experience. I mean, there's a reason why insurers have higher rates for new drivers because, Yeah, for you. Maybe because you watch Netflix. I don't know while you're driving. It could happen. But, there's lots of reasons why people get into accidents. And usually, it's not just one thing. Usually, it's that it was raining and they were texting. Or they had bad tires and they were speeding. Or they were drinking and they didn't know where they were going. Or they got lost because they were drunk, so they didn't know what to do, right? Usually, in the real world, it's not a single thing that causes a behavior, but usually it's a combination of things. I mean, think back to the last personal relationship you had that ended, long-term relationship. Did you break up with that person, or did they break up with you for just one reason? No. It was a combination of things, right? It wasn't just one thing. It's, you can live with the towels on the bathroom floor. Or you can live with the fact that the dishes don't get put in the dishwasher. You can live with 1 or 2, but when it's like 4, 5, 6 things, and pretty soon you get this combination effect where it's just too much, the system is overloaded, and you stop. So that's how the real world works. Now, up to this point, we've been talking about what happens when one variable changes, and we look to see its impact on a single dependent variable. But in the real world, that's not the way things work. Usually there's multiple factors in play at the same time. And so factorial designs are so that we can be systematic about studying how multiple variables affecting behavior simultaneously work. That's what we're interested in. Now, factorial designs are useful for lots of stuff. Not only do factorial designs allow us to design experiments that have better external validity, because if you think about it, if I'm studying people's driving behavior, I want to know how their experience and their familiarity and their level of drunkenness influences their behavior. Because I would bet people who have been driving for 30 years drive differently when drunk than people who've been driving for 30 days. So, we can explore lots of different combinations of things by looking at factorial designs. And we can consider variables in combination that we couldn't consider when we were just looking at a single independent variable. Let's think about between subjects designs. Factorial designs are really cool when it comes to between subjects designs because they allow us to take things that might otherwise just be problematic individual differences, which we care a lot about in a between subjects design, right? Because what's our number one concern in a between subjects design? Are the groups similar enough to compare, right? We care about homogeneity of variance. So if you happen to have a participant group that has a lot of variance, there's lots of individual differences in that group, that can make it really hard to come up with multiple comparable groups. Imagine, for example, that you were looking at different treatments for alcoholism. And you were at a hospital where people had come for treatment for alcoholism. And you had people at that hospital who ranged in age from 18 to 80. Now, you might take a sample of people at the hospital and put them in your study, and then randomly assign them to different treatments for alcoholism. But let's face it, somebody who's an alcoholic at 18 has a really different relationship with alcohol than someone who is an alcoholic at 80. How long have you been an alcoholic if you're 18? Maybe.
A few months.
1, 2, 3 years, maybe. Maybe. When you could actually get enough alcohol to get addicted to it. You're 18. You're not even legal at that point. So you must be getting it from somebody else, but probably not very often. Are you able to get really drunk? Now, if you're 80 years old and you're an alcoholic, how long have you been an alcoholic?
50 years.
Probably 50, 60 years.
Maybe you're just tired of life.
Okay, well, 18-year-olds aren't typically yet tired of life. Okay, so that's a relevant point. People who are 80 are going to respond to a treatment for an addiction differently than people who are 18. I would bet people who are 60 are going to respond differently to a treatment for an addiction than people who are 30. Because if you're addicted at 30, how long could you have possibly been addicted? 10 years? If you're 60 and addicted, you could have been an addict for 40 years. And what treatments are effective for you could vary a great deal, depending on how long you've been addicted. So while it's completely true that the population of people who are addicted to alcohol varies widely, and that can cause a problem if you just draw from that population and hope that you get people who are similar enough to compare. With a factorial design, you can actually make a choice. And you can say, you know what? I'm going to not just look at the different treatments. That's going to be one of my independent variables, where I have treatment A and treatment B and treatment C for alcoholism. But I'm also going to have another independent variable, like how old the patients are. And I'm going to group younger patients together. I'm going to group middle-aged patients together. I'm going to group senior patients together. And then I'm going to look to see if their age actually matters too. Because you know what's possible? It's possible that young patients who've not been addicted for a very long time will respond well to one treatment, and people who've been addicted for a very long time will respond better to a different treatment. Could happen. But the only way I'll ever know that their age matters is if I turn age into another independent variable and actually analyze the data for age 2 at the same time as I analyze the data for the treatment. So effectively what I'm doing when I add this kind of independent variable is I'm reducing the variance. I'm making the groups more similar, right? And the way that they're different is the way that they're different in the way that I mean for them to be different, by age. So if I'm reducing the variance in each condition by grouping people together who have a characteristic I'm interested in. So that actually helps me with my analysis when I'm doing analysis of variance, because I know what the difference is among them, and that's fine. If I just took all of them and treated them as if they were all the same, I could have so much noise in my data that I get a type 2 error. I miss an effect that's actually there because I wasn't looking at their age as a meaningful variable. And when it comes to within subjects designs, our number one concern is sequence effects. We're worried that because the subjects are experiencing more than one condition, that the order in which they experience the conditions could affect their behavior. But when you can use multiple independent variables, you don't have to wonder. You can actually make order a variable. You can say, hey, you know what? I'm going to run this experiment where I've got I've got 3 conditions in this study, like 3 different foods. I'm going to have the dogs eat. They're going to eat different orders. And I know that if I have 3 conditions, that means I have 3 times 2 times 1 different orders. Well, so I just make another independent variable where one order is ABC, and the next level is, so I have ABC as a level, and BAC as a level, and CAB as a level. And then I look to see if there are any, I can use Tukey's test, right? And I can look to see if there are any significant differences between any of the orders. I can actually do math to tell whether or not there were any sequence effects. I don't have to hope that counterbalancing worked. I can show mathematically that it did or it didn't. But I can only do that if I have another independent variable that I can work with. Another thing Factorial Designs let us do that we couldn't do before is have combinations of variable types. So before we either had a between subjects design or a within subjects design. Now we can have a study that has one between subjects variable and one within subjects variable in the exact same experiment. Or we could have one manipulated variable and one subject variable in the exact same experiment. So we call these mixed designs, where we can get combinations of things we couldn't have before that let us explore real-world combinations of variables that can give us good information about behavior. So let's think about some examples. You guys remember the dog food studies, right? You talked to me, it seems like that was like a month ago. 5 weeks, 6 weeks ago. Go back and find those handouts, because you have to remember for this test, you have to be able to identify not only between subjects designs and within subjects designs, subject variables and manipulated variables, but you have to be able to do that. You have to remember, be able to figure out if it's random assignment or matching. You have to be able to tell if the design is complete or incomplete, if the counterbalancing is full or partial, a bunch of stuff from the first unit that we did back in the day before we did all the crazy math. All those factors are coming back into play again. So go back and find the dog food handouts. They're available in the Unit 1 folder if you can't find yours. But go back and find those dog food handouts where I show you different examples of the different kinds of between subjects variable designs and within subjects variable designs, because you're going to need that, because you have to identify those different variables to identify the kinds of new designs you have. So say we start off with our basic dog food study. Okay, we have one independent variable. The independent variable is food type. Now, we talked about this in both a between subjects format and a within subjects format. We talked about how we could have different groups of dogs eat each kind of food, right? Do it as an independent groups study. We talked about having the same dogs eat every kind of food, just eat them in a different order in a related group study. But let's think about what we could do if we have a factorial study. We can switch it up. For example, I could have one variable that's the different types of food, and another variable that's the breed of dog. Because it could be, for example, that small breeds of dogs really like one food more than large breeds of dogs, right? Makes sense. Different breeds of dogs might have different taste preferences if it happened. And so I can have one variable that's breed of dog and one variable that's food type, and I can look to see if there are any special combinations that pop out for me. If I take a look at these data right here, it looks like, in general, which food is preferred, in general, by all the dogs? Chunks of lumps. What a surprise. Of course they love chunks of lumps the best, because it's the best food. And which dogs eat the most? Big dogs. But if I'm taking a look at these patterns of results, my sense is that it doesn't really matter what breed of dog. All breeds of dogs like chunks and lumps the best. But I don't know that for sure until I do a study where I look at different breeds of dogs. And now on my commercial, I don't just say dogs prefer chunks and lumps. I can say all different breeds of dogs, small, medium, and large, prefer chunks and lumps. And that's a more compelling thing to be able to say. Because I've actually done the study where I looked at different breeds to see if breed size had any interaction with food type. I can also use order. So I might have dogs eat all three kinds of food, but then I make order another independent variable. So I have one group of dogs, the green bar dogs, eat chunks and lumps first, then Purina 1, then Kroger kibble. The orange bar dogs eat Purina 1 first, Kroger kibble next, and chunks and lumps last. And the yellow bar dogs eat Kroger first, then chunks and lumps, and then Purina. You'll notice that's a Latin square, right? Each food is appearing in first, second, and third position in one of those three. Yes, you have to remember what a Latin square is. Everything comes back. You don't need to forget anything. But now I can look to see if it matters what order. If you looked at these data, what do you think? Does order matter? Well, there's certainly some variation, but we have to do the math to see. I'm looking at those bars, and my guess is that although there are numerical differences for the different food types, the differences between orders is probably not statistically significant. There's a little bit of difference, but what's more compelling is that chunks and lumps is clearly always the tallest. Purina 1 is clearly second across the board. Kroger kibble is next. But now at least I can say, order doesn't matter. I know for sure. I did a Latin square. I ran the data, and the order that the dogs ate the food doesn't matter. Pretty consistently, they like chunks and lumps the most. So that's mathematically a more compelling story than just I gave dogs the foods in different order, and I'm pretty sure that my counterbalancing worked. I can actually show specifically, mathematically, that the counterbalancing worked and that order did not matter. Factorial designs are cool because not only do they let us kind of build studies that explore multiple variables, but they let us build on studies other people have done to understand the effects that they've discovered. For example, research has been done showing that people who drink, people who've had enough to drink where they're legally intoxicated, will administer a significantly higher shock to a stranger than people who are sober but think they've been drinking. So we're basically talking about the mean drunk phenomenon. You ever met a mean drunk? Somebody who gets to be a real jerk when they drink? Well, it turns out that just in general, when people are actually drunk, they're more likely to do mean things, like shock somebody. They're not actually shocking them in this experiment. They just think they're shocking them. But they're more likely to do mean things, like shock people, when they're drunk than when they just think they've been drinking, but they're not really drunk. So being drunk does make people a little bit mean. Now, it turns out this particular study was done only on men, and we can explore the nature of the effect to see, is this true of men in general, or are there specific subgroups of men that are more sensitive to this effect, are more likely to actually behave this way? So we can divide the group up into men who are smaller and men who are larger. And it turns out if we do this study, and we have small men who are sober and small men who are drunk, and large men who are sober and large men who are drunk, there's one particular group that's significantly different in terms of the level of aggression they demonstrate. Can you see it? Which group is it? Yeah, it's the big men. Big men, heavy men, are more likely, they will administer a significantly larger shock when they're drunk than anybody else. Let's think about that. What does that mean? It's not just men in general, it's big men. Why would big men be meaner drunks than smaller men? Physically smaller men.
Maybe they feel like they can get away with it. Like
Yeah.
that, like nobody will come up to them and like tell them to stop because they're bigger than everybody else. Maybe.
Yeah, what do you think?
Testosterone.
Could have a lot more testosterone in their system. Yep. What happens when a small guy gets drunk and gets in somebody's face? Huh? Huh? He gets his butt kicked, right? He's like, oh, fuck you up, man. And he's just like, done, right? Yeah.
Here's the thing too. I feel like people expect larger men to be more aggressive.
Oh, the joy of toxic masculinity. Yes, the idea that if you're a big guy, then you're going to be like you're going to have more stereotypical manly traits, right? You should have a big ego.
So they might be in more situations.
Right. People might actually get challenged more often, right? I'm going to show. Oh, I'm going to totally impress my girlfriend by going up and getting in this big guy's face, and like he's probably not going to do anything, so I'm going to go whatever. And then if you get this all the time, wouldn't you just get annoyed after a while and just be like, yeah, okay, every time somebody comes up, I'm just going to be like, no. Right? Just leave me alone. Yeah, so we don't know exactly why this happens, but we do see that bigger men are significantly more likely to get aggressive when drunk than smaller men. And that's something we couldn't have learned if we didn't have a factorial design, because we had to be able to look at the size of the person as well as their level of intoxication. So you need to have two variables to make that happen. Yeah.
So, I feel like what I'm about to say doesn't matter. It's if you have like a guy, so you say light men, and you say bigger as far as okay, you have someone that's tall, you have someone like 6'3", and then the bigger guys like 5.
Right, so then the question is what counts as big and small and what counts, yeah. So, I mean, I say, you think about heavy and light, so they're talking about actual physical weight of the person.
Right.
So, yeah, I would be interested to see if it's the same for tall versus short, irrespective of weight.
Right.
Because you might have some tall, really scrawny guy, but you might have some short guy who's like buff, and it's like, he's like, of course, like, that'd be me, in other words.
And you would assume that maybe the bigger guy, but then the reach of the taller guy might be, I don't know.
Yeah.
This for that one.
Right, but this what I'm saying is, with factorial designs, you could actually explore those questions, right? You could figure out, is it just their weight, or does height also matter?
Right.
So do people really take that into consideration? Are they just like, you're physically taller, so you're more likely to be aggressive because you stand out in a crowd, so people are more likely to target you? Or is it an issue of if you appear really muscular, are you more likely? It could also be, you could have somebody who is the same weight, but one is really muscular and one is really fat, and you might find a difference, right? But I would expect someone who's really heavy is going to metabolize alcohol really differently than somebody who is really muscular. So you could see that kind of difference too, yeah.
Right. So what does this do for the dependent variables?
Well, so the dependent variable is the intensity of shock, right, here on the y-axis. So what we can do is we can see how special combinations of independent variables result in differences on the dependent variable. That's what we're trying to do. We want to know not just how does alcohol affect behavior or how does size affect behavior, but how does the special combination of alcohol plus size affect behavior. Does that make sense? Now, when we talk about factorial designs, we talk about them in terms of specific characteristics. So before, when we had talked about between subjects designs, we talked about how there are random groups designs, where we use random assignment to put the people into the groups. We talked about matched groups designs, where we use matching and then random assignment, right? We distinguished those kinds of designs where you have a manipulated variable with ones where the between subject variable is a subject variable. We had natural groups designs. When we talked about within subjects designs, we said you can either have a complete or an incomplete design, right? And that depends on, do you remember? What's the difference between a complete and incomplete design?
Everybody experiences every condition.
No, and within subjects design, everybody experiences every condition. So what's the difference between complete and incomplete? Do you remember? Oh my gosh, it's
So
unit 1.
complete is like when they experience it multiple times.
That's right. Complete within subjects design is where they experience each condition more than once. And an incomplete within subjects design is when they experience each condition only once. Right? Oh my gosh, that's like 5 weeks ago. And you have to go look at those worksheets again. Then there's also the difference between full counterbalancing and partial counterbalancing. Do you remember what the difference is there?
Full is everybody assuming every condition.
Well, that's true in every within subjects design. In every within subjects design, every condition, every participant experiences every condition. So what's full counterbalancing?
Full counterbalancing is when every possible order is done.
That's right. Full counterbalancing is when every possible random order is used. And partial counterbalancing? What's the alternative?
Not every.
Not everyone is used, right? When we do things like Latin square or something like that, where we choose a systematic subset of the possible random orders of conditions and use that. So we have to think about all those things because those are going to be relevant now. We also have to think about how many independent variables I have. It's possible to have 2, 3, 4. As I said, my dissertation had 4. You can have as many independent variables as you can think of, but the more independent variables you have working at the same time, the harder it is to tell what's causing what, right? Because if you have too many factors in play, you can't tell exactly what caused any effect, because there's too much stuff happening. So we tend to focus on studies that have 2 or 3, sometimes 4, but usually not more than that, because beyond that, it's just really hard to tell what the combinations are doing. We need to know how many levels each independent variable has. Of course, the minimum number of levels is 2, right? Because if it doesn't have at least 2 levels, it's not a variable, it's a constant. And we have to know things like, is it independent groups, related groups, is it a manipulated variable, subject variable? We have to know that kind of stuff. So let me show you an example. Let's say that I had a study where I am exploring that classic story that if you're drinking and you have to drive home and you're worried that you've had a little bit too much to drink, you might say, well, let me just have a cup of coffee or 2. I'll sober up and then I can drive home, right? People have this idea that somehow alcohol, which is a depressant, and coffee, which has caffeine in it, which is a stimulant, will somehow cancel each other out, right? And so if you just have some coffee or a Red Bull or something, that'll sober you up and you can drive home safely. Right? It's a little bit crazy. In fact, it totally doesn't work, just so you know. Huh?
That's a good combination.
Well, people do put Red Bull and vodka together because they're like, oh, I know what's going to happen. I'm going to have Red Bull, the vodka, and the caffeine in the Red Bull will make the vodka rush into my system and I'll get like this really quick drunk. And I'm like, no, actually it doesn't work like that. People are just weird. They think of strange reasons to drink bizarre combinations of things. I mean, there are people who voluntarily think of reasons to drink Jägermeister. And you know, that's just, I mean, and I myself personally have done a few shots of Jägermeister competitively. But yeah, I mean, people just drink weird things. For my 21st birthday, we had a tradition where, in my hometown, where there was a street that had lots and lots of bars, and the idea is that you would start on one end of the street and drink your way down the street. It was called the mall crawl, because by the time you get done, you're actually crawling, because there were a lot of bars. And on your birthday, you got to drink free.
Oh my God.
Yeah.
Where were you?
Boulder, Colorado. Yeah, you can start at one end of the Pearl Street Mall and drink, and it's outdoor. It's an outdoor like walking mall. So like it's beautiful outside. You're walking and you walk in. You're like, it's my birthday, and you drink free. Of course, the idea is that you bring all your friends with you, and they all have to pay for drinks.
Yeah.
Right.
So they don't care as long as all your friends come. They're like, sure, you can have a shot of whatever you want. We don't care. So the idea is you pick a drink and you stick with it, right? Because you don't want to be mixing up your drinks if you're going to like 15 or 20 bars. You're gonna be like, you're gonna be messed up, right? So here I was, I thought, okay, I'm super cool, I'm 21, I'm gonna do this. And I'm like, I made the biggest mistake of my life, which was I picked tequila. So I started at one end of that street, and I walked way down. I'm going, and like, they're like, what's your drink? And I'm like, tequila. And they're like giving me shots. And then at one point, I walked into this bar, and they're like, oh, we have a special tequila shot. It's called a Prairie Fire. And at that point, I probably had 4 or 5 shots. I'm like, sure, that sounds great. Let me have that. Well, Prairie Fire, turns out, is a tequila with a shot of Tabasco in it.
Oh my God.
And this is what made me think of the story. The people drink weird things on purpose, and I was drinking this weird. It's called a Prairie Fire, and I thought, oh, this would be totally fine. Okay, if you had like 7 or 8 shots of tequila, and then you shoot Tabasco sauce. Let me tell you, you get really sick really fast.
Oh my God.
And I didn't drink tequila for like 20 years after that because I was sick on tequila that whole night after that Prairie Fire. Oh my God, every time I got sick, it was like half Tabasco sauce. I swear, it was the grossest thing ever. So, yeah, all I can say is people drink weird things. And Tabasco sauce and tequila, not something I would recommend, especially if you've already had a whole bunch of shots. And you're there with all your friends, and they're like, drink, drink! Yeah, 21-year-olds don't make good drinking decisions at all.
Oh, wow.
So, huh?
That's crazy.
It's burned into my memory, huh?
Tabasco hot sauce at that. Tabasco is pretty like super intense. Not even like Louisiana, like kind of mild. Texas Pete, kind of mild.
No, no. I don't know what this was. It was basically air fuel in a cup. I don't know what. It was the most brutal thing. They're like, it'll burn all the way down. It's great. And I'm just like, sounds great. Let's do it. You know? People are weird when they're diverse. Don't do that. Bad idea. So everyone says, hey, you want a Prairie Fire? Be like, no. Bad plan. Okay, unless they're like, it's cool, I'll give you $500. Then think about it. Competitive drinking. All right. So let's imagine that we're doing a study to see if that thing actually works, where if you have coffee or some caffeine, it'll actually mitigate the effects of alcohol. So we're going to have one independent variable that is alcohol. We're going to have 2 levels where people either are drinking alcohol to the point where they are legally intoxicated, or they don't drink alcohol. So they might think they're drinking alcohol, but it's not actually an alcoholic beverage, and they're not actually getting drunk. We have another variable where people get various amounts of caffeine. So they might get 400 milligrams of caffeine, and that's about 2 cups of coffee. Or 200 milligrams of caffeine, that's about 1 cup of coffee. Or they might just have water with no caffeine in it at all. Now, the first variable has 2 levels. That's important. You want to make sure they keep track of 2 levels. Then it's between subjects, because people are either drunk or they're not, right? We're not going to sober them up and then do whatever we're doing to them again. They're either drunk or they're not. It's a manipulated variable, and we use random assignment. We're just going to assume that we use random assignment unless otherwise specified, because random assignment is preferable, because it gives us the best statistical chance of distributing individual differences across the different conditions. So it's a manipulated variable, random assignment. So that's our first variable. Our second variable has 3 levels. Okay? 400 milligrams, 200 milligrams, and 0 milligrams of caffeine. It's also between subjects, manipulated because I can randomly assign people to how much caffeine they get. So I would say, looking at this information, knowing that I have 2 variables, one has 2 levels, one has 3, they're both between, they're both manipulated, I use random assignment for both, I would call this a 2x3 random groups factorial design. Now how did I get that? Well, where do you think the 2 and the 3 came from? The number of levels, right? And where do you think the random groups part came from? Random assignment, right? And factorial means that this is a design that has multiple independent variables. So if anybody says, oh, we did a factorial design, they're telling you right away they had multiple independent variables in their experiment. So you guys are right on. Okay. The first number is the number of levels for independent variable 1. The second number is the number of levels for independent variable 2. Now, if I had 3 independent variables, I would have something like a 2 by 3 by 3 factorial design, right? You just keep adding numbers as you have more variables. My dissertation was a 2 by 2 by 2 by 2 factorial design because I had 4 independent variables and each of them had 2 levels. So we know that it's a factorial design because there's more than one independent variable, and the fact that subjects were randomly assigned to all the conditions in the study allows us to call it a random groups factorial. Now if you take a look at the handout I gave you, I know handouts! Handouts are so great. If you take a look at the handout, you can actually see how we come up with these kinds of things. So first question you want to answer when you're looking at a particular experimental design is, what kind of independent variables do you have? Well, our choices are, they're either all between subjects, I have at least one of each between and within, or they're all within subjects. Okay, in this case, we had all between subjects. So we're going to stay over here on this side of the chart. Then our next question is, are the independent variables manipulated variables or subject variables? And we said manipulated. So that means we're going to continue to stay over on this side of the chart. So we're going to go to manipulated variables. Next question is, how were the subjects assigned to the different conditions? Well, the options are, they were either randomly assigned, or we did matching and then random assignment. And we said that it was all random assignment. So that means what we had is a random groups factorial design. And as you see, if you look across the bottom of this page, there are lots of different kinds of factorial designs. Random groups factorial design, matched groups factorial design, natural groups factorial design, a P and E factorial design, that's what this one's called, a P and E factorial design. Incomplete repeated measures with full counterbalancing, incomplete repeated measures with partial counterbalancing, or complete repeated measures factorial. And you flip it over, there's even more. There's mixed factorial design, another P&E factorial, a pretest post-test factorial, natural groups pretest post-test factorial, or a natural groups factorial. So there's all different kinds of factorial designs, and you will need to be able to recognize different types of designs depending on the kinds of variables you have. So if you're like, oh, I don't remember anything about whether, I don't remember anything about incomplete or complete designs. Yeah, go back and look, because you're going to need to know. I'm going to give you descriptions of studies, and you're going to have to say, okay, the first independent variable is between, it's manipulated, they use random assignment because nothing else is specified. The other variable is within subjects, and it's a subject variable, and then you're going to have to be able to figure out what kind of design it actually is. That's the design type. Factorial notation is it a 2 by 3, a 2 by 2, a 3 by 2, a 4 by 3, whatever numbers you need before that. So I will ask you to identify studies in terms of their factorial notation, which is the numbers part, and the factorial design, which is something from this flowchart. Now, if we try again, let's get this to come back up here. There's one for you. Take a look at your flowchart and see if you can figure out the factorial notation and design type for this study. When you think you have the answer, don't shout it out. Who thinks they know the notation? That's just the numbers part. David.
I think,
We're just the notation now, just the numbers.
hold on. So it would be
You wanna do the other
three,
part?
Yeah, but 3 by 3.
It's a 3 by 3, right? We would agree it's a 3 by 3? Okay, and we know that because each of the independent variables has 3 levels. And there's only 2 numbers because there's 2 independent variables. Okay? So we've got a 3 by 3. Now we have to figure out what kind of 3 by 3 design it is. Corey has an idea. What do you think, Corey?
P by E factorial.
A P&E factorial design. What do you guys think? Why is he right? What's relevant to making a P&E factorial design? Hmm? What kind of things do you need to make a P&E factorial design?
Within subject variables and one. Okay, you need manipulated and subject variable.
You need to have one of them be manipulated and one of them be a subject variable. P&E factorial design is the only kind of design that actually shows up on both sides of the page. Okay? Because as long as you have one subject variable and one manipulated variable, you've got a P&E factorial. P&E stands for person by environment. And the idea is that you're going to take some subject variable, that's the P variable or the participant variable, and you're going to take someone because of some naturally existing state and put them in a manipulated environment. So you've got the subject variable, which is the P, and the manipulated variable, which is the E. So a P and E design, P by E design, or P and E design, always has one subject variable and one manipulated variable every time. Doesn't matter whether they're between subjects, doesn't matter whether they're within subjects. If you've got one one subject variable and one manipulated variable, you've got a P and E design. So 3 by 3 P and E factorial design. And on the problem set for this unit, there will be little descriptions of studies, and you will have to do that where you figure out the notation and the design type. So you can go practice that if you want to with this flow chart. All right, so let's go back to this study we were talking before with alcohol and caffeine. Now let's imagine that what we're going to do is have different people experience different combinations of these 2 drugs. And then what we're going to do is put them in a driving simulator, because if we're going to get people drunk on purpose, we can't actually put them out on the road. That would be bad. We can't put them in a driving simulator and see how quickly they respond to stimuli that they might have to respond to on the road, like a car pulling out in front of them, or a kid chasing after a ball, or a light changing color, or something like that. Now, in this case, because I have a 2 by 3 factorial design, we can actually think of that as a mathematical formula. If I have a 2 by 3 design, that means that I have 2 times 3 conditions, different conditions in my study. There's 2 times 3 different possible combinations. So that means this study has 6 different conditions, because I've got one condition where people get no alcohol and no caffeine, one condition where people get no alcohol and 200 milligrams of caffeine, one where they get no alcohol and 400 milligrams of caffeine, and then I have the similar conditions but where they've gotten alcohol. So there's 6 different possible combinations of the different levels of the IVs in this study. That means that we're going to have means in each of those conditions. So in a factorial design, a 2 by 3 factorial design, I'm going to be doing analysis on 6 different means. Okay? 6 different means. If I had a 3 by 3 factorial design, I would be doing analysis on 9 different means. So the most we've done up to this point is 3 means. Now we're talking multiples of that, right? We're going to get the very fewest you can have in a factorial design is 4, because you have to have 2 independent variables and each one has to have at least 2 levels, right? So 2 by 2, that would give you 4. So the fewest means you're ever going to be looking at in this unit is 4, but more often it's going to be 6. Now, when we do factorial analysis, we're doing ANOVA, again, because we have more than 2 conditions. We're always going to have at least 4 in a factorial design. So ANOVA is appropriate. But we're going to have to do multiple analyses of variance every time. We have to do one ANOVA for IV1 to see if it has an effect on the dependent variable. We have to do another ANOVA for IV2 to see if it has an effect on the dependent variable. And then we have to do a third ANOVA for the combination of IV1 and IV2 to see if the combination has an effect on the dependent variable. Now, nobody in the real world ever hand calculates factorial ANOVA because there's so many of them to do. And you guys know how long it takes you to crunch through one analysis of variance. You don't want to have to do 3. There's not enough time. And since nobody would ever really do it, I'm not going to make you do it. I'm going to teach you some shortcuts, some tricks that people use when they're looking at data to figure out if they got significant effects or not. And we're going to practice looking at graphs of factorial designs and trying to figure out if the graphs suggest there are main effects and interactions. Because I know you guys can look at a statistical statement and I can tell you, you know that there are degrees of freedom and an observed value and you can tell whether it's statistically significant or not. Now we want to practice looking at graphs and other things like tables and see if you can tell from the data in the table whether or not something is significant. So first, we're going to talk about what are called main effects. Main effects are the effects of single independent variables on a dependent variable. So in our study where we're looking at alcohol and caffeine and the effect of alcohol and caffeine on driving behavior, we have a possibility of 2 main effects. One is the main effect of alcohol, and the other is the main effect of caffeine. So up to this point in this class, we've been talking about main effects. We just didn't call them that, we just said it was an effect, because there was nothing else for it to be. It's just an effect, right? If I look to see if the kind of food dogs eat influences how much they eat, we're just talking about a main effect of food type, but it's just an effect because that's the only thing we're looking at. But now we have to think about not just individual effects, but combinations. So we distinguish those effects of individual independent variables from those of combinations of independent variables. When you have a single independent variable and you do an analysis, you're looking for a main effect. If you get a significant result from your statistical analysis, then you can say there's a main effect. That means there's a significant, statistically significant effect of that independent variable on the dependent variable. If you don't get a significant difference, then you don't have a main effect. It means there's no effect, right? It doesn't matter. So main effect is a significant effect. In this study, we could have a main effect of alcohol, which would mean that alcohol affected how people drove, whether they were drunk or whether they were sober. There was a significant difference in those 2 groups of people. We could also have a main effect of caffeine, meaning that how much caffeine people got influenced how they drove, such that people who got 400 milligrams drove differently than people who had 200 milligrams drove differently than people who had 0 milligrams, for example. Both of those describe main effects. But when you talk about a main effect, you're just talking about the effect of one independent variable on the dependent variable. The alternative is interactions. And interactions are always about combinations of independent variables. So if I say that there's an interaction between alcohol and caffeine, I'm saying that a special combination of alcohol and caffeine resulted in statistically significant differences in subjects' behavior compared to other specific combinations of alcohol and caffeine. Maybe people who had, the least alcohol and the most caffeine responded very differently than people who got the most alcohol and the least caffeine, for example. And if there are significant differences between particular combinations, then we can say that there's an interaction of the two. That something about having both of those chemicals in your body at the same time results in different behavior than if you just had one or the other. So, anytime we talk about an interaction, make sure you're talking about multiple independent variables. You can't say there was an interaction of alcohol. That doesn't make sense. Or you can't say there's an interaction of caffeine. You can say there's a main effect of alcohol. You can say there's a main effect of caffeine. But if you say there's an interaction, you have to have at least two variables in that sentence. So there was an interaction of alcohol and caffeine. All right, so let's take a look at some data. I told you we would have 6 different conditions. We would be looking at 6 different means. So here are some means. This is some made-up data. We're just going to use this to practice a very simple technique for identifying potential main effects in interactions. This is a technique that scientists use when they're just looking at a paper. They've got the means. They haven't gone through the whole results section, but they want to just kind of look at the means and imagine the pattern of results. So I'm going to teach you this technique. It's pretty easy. First thing you need to know is, as I said, we've got 6 conditions. So we've got 6 different means. 6 different groups of people had 6 different average responses to